Good morning, friends. It's Ben again. I am actually recording this barely in the morning on Tuesday, the day that we don't have classes. With regard to that, you'll notice I'm in my luxurious office here. It was quite slick this morning. I see why they didn't want to have the campus opened up. So, but in any case, though, recording some stuff here so that you can watch it at your leisure when your connection is good and stuff like that. Okay. So if you recall, the last thing that we were doing when we left, I guess that was Thursday, was taking a look at conditional probability. And the thing that we said was that with conditional probability, you are taking the probability of an intersection and then dividing it by the probability of whichever one of the two things appears after the bar. So we read it as probability of A given B, okay? And so we'd done a calculation here about false negatives and false positives for the ELISA test that screens for HIV. And now we're going to take a look at something different. Now, with regard to this, notice, I want you to catch that we are not always going to have a table laid out for us every time we do something with conditional probability, nor do we, every time there is a table, assume that it's going to be conditional probability, okay? But I feel as though it's just a really convenient way to see these particular ones, all right? So the data here is about a study of men who have died and the question of whether they were a cigar smoker when they died, and the question of whether they died from cancer or not. So as you can see on this, we have a total of a large number there, 137,243. So that would kind of go over here, all right? And then we're going to need to consult the totals on columns and the totals on rows as we go along this. So I figure it's probably easiest to just do that as it goes along. So I'm totaling up that row there, that first row, and I get 1,041 on it. And I said row, and then I did column. Sorry. But so then 7, 2, minus that. So I should get 136,229 on this here. And then going across with 20747 plus 782, 121, 529, 91 plus 7757, 78, 48, and then 141 plus 7725, 7866. All right, so we're running along with these, and the first question asks us, what is the probability that a randomly selected individual from the study who died from cancer was a former cigar smoker? Okay, so they died from cancer and they were a former cigar smoker. So those are the things that we're thinking about. The one thing that's in the intersection is going to be those 91 men there. And then out of, so the out of, we have to look and see which one we were given. So reading carefully, what is the probability that a randomly selected individual from the study who died from cancer was a former cigar smoker. So that means we're looking at the ones who died from cancer. And that means that we will say out of 1041. Now, I think that's a good enough number there, but often it helps to get approximations. And so that looks like about 0.087, all right? Then what is the probability that a randomly selected individual from the study who was a former cigar smoker died from cancer? See how that switched things around? So this time you know they're a former cigar smoker. And so there's 78, 48 of those. And how many of those died from cancer? And that is still the 91. So if we do the division there, 91 divide 7848, we get 0.012. Okay. So notice that means there is a lot smaller probability coming out for the second one. And so we have to see that these things are different. In both cases, you're taking the intersection to get the numerator, but then your denominator is determined by which thing you knew about them first. If, on the other hand, you were just asked what's the probability that somebody selected at random was a former cigar smoker and died from cancer, you'd say 91 out of that 137,243. So different things depending on what the purpose is here. Yeah, so then the quick question here of, do the events never smoked cigars and did not die from cancer appear to be independent? Now, the calculations we just did don't really establish those. What we need to do for that is to either get the probability never smoked, we need to get the probability about never smoked cigars and did not die from cancer, and then the probability that, and then the conditional probabilities of one, the other, or both there, okay? So what I'm going to do is to get the probability of didn't die from cancer, so not cancer in this, and looking up there, did not die from cancer, we've got 136,229 out of 137,243. Okay, and I will have to get a calculator to do that. And divide 137,243. So we get about 0.993. Okay. And then the probability not cancer given no cigars. And as per usual, everything always kind of shoves too far to the side. So I've got to get that a little closer here just to have the room. Okay. So probability they did not have cancer and they did not smoke cigars. So that means that we have to be in this column here and did not smoke cigars. So we have to be in this row here, right? So that means we're going to have the 120,000, where am I? 747 out of, given they did not smoke cigars. That's the 121,529. Okay, so both of those numbers are super close to 1. So let's see what happens. 120 747 divide 121, 529. Okay. And the bad thing here is that if you don't know how to round correctly, this could be misleading. So the number that I get here is 0.994. Okay. If I expanded out those two numbers, the first one is actually 0.992611645, but the important part is the 0.9926. Okay. Whereas the second one is 0.9935653219. The important part is 0.9936 about. So those two numbers do not agree. And so that means that these events are not independent. Now, are they close enough? We will talk about that later with a goodness of fit test using something called the chi-square distribution. But for now, we're just, So the independent portion of it is just about the two events A and B. If two events are independent, then having information about one of them doesn't actually give you any information about the other one, okay? But if they are dependent, it means that you've got something that's a little bit more likely or a little bit less likely, depending on whether it happened. All right. So we're going to take a look here now at a quick example at the bottom. And it's, it's not anything super complicated, but we're rolling one six-sided die. So we get numbers 1 through 6, right? So we're going to look to see that these things are not independent by calculating probabilities. So one thing that you can do here is to say your probability of A, which you can get real quick, is just 1/2. And then you do the probability of started to do the wrong one there, probability of A given B, okay? And when you do the probability of A given B, you look at the intersection of them. There's only one thing in both. And then that's divided by the number of things in B. Oh man, that's looking wrong, isn't it? I made up this example real quick, and it looks like I might have actually made up two events that are dependent or that are independent here. If we looked on the other hand of saying something about the probability of B, and we see that that is going to be 1/3, and the probability of B given A, then we can see that there's only one thing in the intersection, and there's 3 things in A, so we end up with a 1/3. Man, so that badly written problem turned out A and B were independent, okay? And now let's see about the probability of A given C, right? So this note over here, A and B independent. Okay, then the probability of A given C, when you get a look at the intersection, there is actually nothing in the intersection of those, 0, out of given C, so there's 3 things in C, so your probability is 0. The probability of A given B, or A given C, and the probability of A are not equal, so A and C are dependent. Okay. Then, since we've also got the probability of B, let's get the probability of B given C. And when we look there, there's one thing in the intersection of those. And we're given C, so that's out of 3. So we ended up with 1/3. And we also know from looking before the probability of B is 1/3. So the probability of B given C is going to turn out to be 1/3 if we go ahead and do the other thing of getting the probability of C given B will turn out to get 1/2 on this. So what we have found out is that B and C are independent. Okay, and is there a pairing that we've not tried here? Yeah. Now, this does end up with a weird sort of thing, right? A and B are independent. B and C are independent, but A and C are dependent. So it doesn't, if you talk about relationships between them, you don't have the transitive relationship that independence, goes across there. So yeah, that's just a little factoid piece there. Okay. So hopefully that gives us kind of an example of checking dependence and independence. And now we're going to try to look at an example here where we use the dependent idea, and we can talk about the independence as we go along here. This is actually, I think, was supposed to have been an example for the section about conditional probabilities. So sorry if those are popping up in the wrong place and stuff. But 2 cards are drawn from a standard poker deck without replacement. We're going to find the probability of drawing 2 hearts. Okay. So our probability that we get the first is a heart, and the second is a heart. Okay, that is going to be the probability that the first is a heart. I'm just going to write H for heart, times now the probability that the second is a heart given that the first was a heart. All right, so grabbing these and pushing them over here a little bit, maybe pushing them together a little more. So our probability that the first was a heart, we're going to look at the poker deck and say that we have 13 hearts out of 52 cards, right? And then the probability of the second one being a heart, if we had replaced that heart, we would again have 13 out of 52. But this was without replacement, so we will have 12 hearts left, and it'll be out of 51 cards. And if you want to go ahead and get the number for that, you can. I'm going to get this on my calculator real quick, and I kind of like the fractions part. It ends up being 1/17. And if you'd like a decimal out of that, it's about 0.059. Okay, so yay. Then if we do the probability of drawing a heart and then a club, that's the probability that the first is a club, and the second is, oh, I did it backwards. This one's supposed to be the club. And so this one is supposed to have been the heart. Okay. So doing it the same sort of way, the probability that the first is a heart times the probability that the second is a club, given that the second, or that the first was a heart. First was a heart. Okay. So the first one was a heart. We've already done that, 13 out of 52. Now the second one being a club, given the first one was a heart. That means that we still have 13 chances here because we didn't take away any clubs. And then that's out of 51. So let's see. 2 and 51. And the fraction of that is not as nice, 13 out of 204, but the decimal of it is about 0.064. Okay, so slightly higher probability of having that happen because there were more clubs that were left in there. Okay, so hopefully that makes sense. So the next one asks us to find the probability of drawing a heart and then drawing an ace. So we're going to write down the probability that the first is a heart and the second is an ace. Let's see, the A is not going to get confused with anything, so that should be fine. So the first is a heart, 13 out of 52. And then the second one is an ace. How many aces do we have? Well, it depends. Did we draw an ace of hearts or did we not? That's the problem there, right? So what we have to think about is maybe drawing a diagram here and looking at all of our situations. Okay, and my situations, I think I need to draw 4 of them. Okay, so the first situation then is going to be that you drew the ace of hearts. And the second situation is that you drew another ace. Okay. And then the next situation is that you drew another heart. And then the last situation is that you drew, it seems like I've actually gotten all of my possibilities in line there. Have I forgotten? Different ace, different heart. Oh, other, not heart, not ace. Okay. So we'll have to break it down into those 4 possibilities, which are mutually exclusive, and then add up what happens there. Okay. So when you I'm sorry, folks. I've thought this through the dumb way. Okay. And I needed to erase these. Okay. So the first one had to be a heart. Sorry. So you had to either have the ace of hearts or the non-ace heart, right? Because we are assuming that we had that we had drawn a heart there. We don't have to break it down into the possibilities of drawing a heart or not drawing a heart, because if we didn't draw a heart, then we are stopping the whole process. So I'm just writing down the probability the first is a heart times the probability the second is an ace, given that the first is a heart. Okay, so 13 out of 52. Okay, so if we know that we've got a heart, then out of the 13 possibilities, 1 is an ace, and the other 12 are not aces. Okay, so we'll have the 1/13 here times, and now we have to think about what our numbers end up being. We have drawn the ace of hearts. That means that we have 3 aces remaining, right? out of the 51 cards. And then the other possibility out of the 12 13s there. So on that, you have to think, how many aces do we have remaining? All 4 of them out of the 51 cards. So again, I have to turn to the calculator for this. So 13 50-seconds times, and let's see, we'll have 3 divided by 13, 51 plus 12 times 4 divided by 13 times 51. I think I got that right. And so fraction-wise, after simplification, that turns out to be 1/52, which is about 0.019. Okay. So anyway, I wanted to have an example like this where you have to stop and look at the branching possibilities. But then when I started thinking it through, I tried to make too many branches, and we didn't have the possibility that it wasn't a heart, because we'd assumed our given part that we'd gotten a heart on that first one. Okay. All right. So the next bit here, we're looking at tabulating a survey of 1,456 people. And kindly enough, I went ahead and did the totals here. And this one, we're going to get the probability that a randomly chosen person favors the gun law. And so if you want to do that, you can just say how many favor the gun law out of how many who were surveyed. So 1041 out of 1456. All right. And decimal wise, that's 0.715. Okay. Then the probability that a randomly chosen male favors that. So for that, we're going to have to be here, so 342 out of the 633. So 392 out of 633, which you can probably see without actually doing the calculation, is going to turn out to be a little bit different. So about 0.619. And the probability that a randomly chosen female favors that. So that's the 649 out of 823. So 649 out of 823. 649 divided by 823. We're getting about 0.789. Okay. So the question is, what does this tell you? The numbers that you're getting here don't agree at all. And so that says that the probability of favoring this gun law depends on whether you're male or female. Now, it's not saying that is an absolute causal thing, right? There are females who oppose the gun law, and there are males who favor it, and there are males that that oppose it, and females who favor it. Those numbers are there. It's not absolutely deterministic, but if you know one, it changes the probability about the other. Okay, so the thing that we are getting out of this is that because probabilities differ, and these are dependent. And as usual, not get enough room there. All right, so we end up getting something that's dependent, and it just says that the probabilities are different. It doesn't say that being male or female causes you to favor or oppose the gun law. It doesn't say that favoring or opposing the gun law makes you male or female. We are not assigning causality on these, right? Causality is really the realm of the actual sciences as opposed to math and statistics. We are just making the observations there. All right, and I think this might be the last one. Yeah, so this last one here, we're given a written out problem, and we're wanting to look about what we've got on that. And this, like with all of them, it would be a good point for you to pause and see if you can parse this one out on your own. But it says a researcher finds that of 982 men who died in 2002, so that's going to be the total number from the study, 221 of them died from heart disease. Also, of those 982 men, 334 had at least one parent that had heart disease. A man is randomly selected from the group. Given that neither of his parents had heart disease, find the conditional probability that this man died of some heart disease. So let's see what happens here. All right, so I'm going to try to lay this out in a table. And so here I'm going to say had heart disease. Should probably phrase that stronger, because it wasn't just that they had heart disease, but they died from it. And so, oh man. So, died of heart disease. Died of other cause. Okay. And then we're going to look across here and do parent with heart disease. And then we'll do no parent. I can't spell parent with heart disease. Okay. And because of the way things are discussed, we've got some totals to work with. And so let's see what we can write down. So we have 982 men total. And 221 died from heart disease. So 221 died from heart disease. And 334 had at least one parent who had heart disease. So 334. And we can go ahead and fill in some other parts here by subtracting. So 982 minus 221. So 761 goes here. 982 minus 334. We've got 648 that goes here. Now, given that neither of his parents had heart disease, find the conditional probability that this man died of some heart disease. So so neither of his parents had heart disease. That means that we are in this category here. How do we apportion those 648? There is no information about that. It didn't tell us the proportion of any of these. If it had told us even one of the intersections, we could have kind of puzzled out and figured out how many go in each category, right? But this didn't give us that information. So technically, we don't have enough information to finish this problem. However, if you were working in some field where they expected you to get results, what you would have to do is to write down your assumptions. And the only assumption that we can really make here that gets us any progress is the idea of what if those things are independent. If they're dependent, we don't know how much it changes things. But if they're independent, we can kind of do something. Okay. So then we'll write down here, just technically not enough info. But assuming these events are independent, then we can go ahead and do something, right? So if we are going ahead and doing that sort of thing, then we can go ahead and figure out probabilities all across the board here. So the 221 out of 982, that would be about 0.225. Okay. And that means that the other part would be about 0.775, right? And maybe what I'm going to do is to mark this part in red because, you know, I'm doing something kind of dangerous here with my assumptions. And then I'm going to just grab all this and push it upward a little bit there. Yeah. And then for the parent with heart disease, divided by 982. So that one, we're getting 0.340, which would mean that this other one ought to be 0.660. Okay, those are approximations and stuff. So if those things are independent, then we can go ahead and multiply in order to get any of these. So for instance, this one here, the probability is going to be the 0.225 times the 0.660. And so we would get 0.1485. So I'm going to put 14. I'll go ahead and put 149. Okay. And then the 0.775 times 0.66. Here you get 0.512 roughly, right? And then going ahead with the others, 0.340 times 0.225, you get 0.077 here. And then you could just do subtraction to get the other parts, but doing subtraction with the calculator is no harder than doing multiplication. So, you know, 0.264. Okay. Now, if those don't add up correctly, right? The reason they don't add up correctly is because I rounded. It's not that somehow the laws of probability have broken and that, you know, everything's wrong and you can just do whatever you want. It's just that I've rounded things so they may end up being off. But the question asks to find the conditional probability that this man died of some heart disease. Oh, sorry. probability that the man died of some heart disease, we can calculate, and we don't have to do all this stuff here, right? If we are assuming independence, probability the man died of some heart disease is going to be the conditional probability is going to be the 0.225. If you wanted to get if you want, the reason for that is that if we've assumed the independence, then in getting the conditional probability, you would end up taking this 0.149 and dividing the 0.225 that we just multiplied in order to get that, right? But in any case, I've actually shown you more than you actually need here, because we've both looked at how you would get the probability that he died of some heart disease, and that he did not have a parent with heart disease, but also the probability that he died of some heart disease with no assumptions, because independence would be making no assumptions, right? But in both cases, we've made an assumption and we better write it down. And this makes it super annoying if we then later get quoted out of context and they don't put our assumptions in there, because it may look as though we didn't realize that we were making an unwarranted assumption. So anyway, that gets us through some examples with the ideas of conditional probability and the idea of independence. And so the next thing that we're going to tackle is going to be Bayes' theorem. Okay. All right. I will see you all later on. Thanks.